Welcome to the third part of our exhaust treatment workshop. I will now finally show you how to simulate the flow, molecule movement, and the chemical reactions to our catalyst channels. First I will open the structure that we have created in part 2, and then I will crop this a little bit so that the simulation does not take up too much time. Therefore, we click here on right click on structure and go to process crop. And here you can preview crop. So if you change any values here, you can instantly see how would your result look like. Crop down until we have only one unit cell of our structure left. This is enough to simulate because it is repeating in each direction. So click on run, and here you have it, only one cell. Okay, and next thing we want to do now is to simulate flow, and this is done by predict. And here we have different options. We have Stokes and Navier-Stokes, and in our case also Brinkmann. Stokes flow is a little bit faster for solving, but it's not meant for fast flows. And Navier-Stokes can solve fast flows, also like this one which we have in our catalyst packings here. But it will take a little bit more time for solving, and it's not there's not enough time for this in our workshop today, but you can still try and use the Navier-Stokes version if you have some time for testing it out. We will now go for Stokes Brinkmann, but you can do all the same settings also for the Navier-Stokes. And no matter what solver you choose, we also, in both cases, I would recommend using the Lear solver here. So the first of these two options. Okay, so, and then click on edit, and we have this dialog for our flow settings. And the first thing that we have to do is to we have to define our undefined material here. So our wash code material is undefined at this point. So I click here on this button, and then I can go and tell Geodic that I have a porous media filled with air. So our flow is also moving inside our green material. I hit OK, then I can see here both are activated for air. This is our phase that's flowing. So all right, and then go to permeability, and we have to type a permeability here for our porous material. And for this I will take 1e-7. 1e-7, this is a rather high permeability. Don't get confused by this small value of the number here, but for a permeability value this is rather high. So flow can go through this green material more easily. So we have materials where it's much harder to get through. Okay, so next tab is the boundary conditions tab. I already told you this structure is periodic in all directions, so we can change periodic here, and it will be okay. We can now deactivate this add implicit inflow region, that. And for Stokes, we will say mean velocity 2 meters per second. If you use Navier-Stokes, please type in pressure drop 10 Pascal. All right, then in solver options we don't have to change anything for the Stokes solving. If you use Navier-Stokes, then normally this use multigrid is turned off. You can turn that on, and the relaxation is also not 1, some kind of a smaller number, but you can also type in 1 here, also for Navier-Stokes. Yeah, and that's it, setting up the flow. Now I will click on run and see what happens. So this should work rather fast for our Stokes flow. Here we have it. It's the results file. Here you can see, for example, for our 2 meters per second flow velocity, we have a pressure drop of 9 Pascal. And now click on flow visualization to load our flow field. I will load all the fields that are in this file. Okay. Then we can see how our flow velocities look like. Yeah, what you can now see is we have colors in our structure and we have colors in our flow field. So I will quickly change our structure to be black and white here. So I use some gray colors, and then it cannot be confused with the velocity. And if you now have a look here at our values, you can simply hold your mouse over it, and you can see here in the middle we have some velocity of 7 meters per second or faster. And this is totally normal because the mean velocity is calculated over our whole surface here, surface area. But there are for sure some places where there's no flow possible. So here the velocity is 0 because we assume that there's no flow here in our monolithic structure. There's only flow in our wash code. So if to have a mean value of 2 meters per second on this whole surface, there surely have to be some points where there's a higher velocity, and this is here much higher than the 2 meters per second that we have specified. It's totally normal. If you now aim at the wash code, you can also see there's velocity inside the wash code. And if you want to see field here, you can also deactivate our structure and see values everywhere. So don't forget, there's also flow going through our structure, light gray inside our porous material. There's also flow. All right, and that's it for the flow, more or less. We can now go and simulate our movement of molecules. This can be done predict module. Here I click on edit options, and before we change anything here on the first tab, we go to the solver tab and we load the flow field of our already simulated velocity profile here. So here on flow solver, you can choose the different kinds of solvers, but you can also change it. Load from file, what we do now. You click on load from file, and then we browse for our Stokes result that we have recently created. Okay, open that. Here you can see automatically GeoJIT knows how much velocity did we type in for our flow simulation. And now we can go back to the first tab for the experiment. And what has changed here is that we cannot change the flow boundary conditions anymore, because this is all defined in our first simulation run here, which leaves us to simply change the time, and I will change it to 0.1 seconds. This is enough time so that all the particles can flow through our channel and get to a travel distance of at least 10 centimeters. And time step is 0.001. This will give us more or less how precise are the measurements at the end in our result viewer. Particle boundary conditions I will change all to periodic, just like in the flow simulations we have the periodic conditions also for the particles. And then we can go to the particles tab and set up the adjustments here. Okay, so first the initial particle parameters. Where do our particles start? Inflow plane, that's all right. but we will change the particle positioning weights, the velocity, which means that if you take a look at our velocities profile, this red section is in the middle, there's a higher velocity, and here we will start more particles than in the lower velocity regions, because this will lead to a constant particle volume concentration inside our flow. This is typically what we have in a good mixed airflow. So change this to velocity and then go down with the number of particles to 500. Because again, we do not have so much time today for our workshop. Can surely do that at home with higher values, but then we'll have to wait a little bit longer. So, and then finally, particle end positions. We will activate this last point, stop at maximum displacement here, and say 0.1 meters. That means if a particle has reached the distance of 10 centimeters, so 0.1 meters, it will stop there. And this is a trick to do a channel length simulation of 10 centimeters, but our model here is only 3 millimeter long. So just by using the periodic boundary conditions, this is a much faster simulation time. All right, movement. We do not have to change particle movement options here. On the interaction model, we have to change this porous pass-through model to all particles pass, because we want that our molecules can enter our wash code. And then, of course, we have to change our particle diameter from finite size to molecule size. Make sure they don't have a certain diameter. So we assume particles with no diameter equals 0. Okay, so next thing is to type in our diffusivities. It's done in the size distribution table, and then if you go here, see diffusivity in pore, that means diffusivity in the pore flow. And for this we can simply get the values from literature. So for air, take T.5. And this one here, diffusivity in media, so this means inside our wash code. Here we can take the results from our Knudsen diffusion from step 1, which is approximately 3e-6. So this is the diffusivity inside our inner or between in the pores of our wash code layer. All right, that's it. Okay, run. Let's see what happens now. May take a little bit longer than the flow simulation, but not much. See, we are tracking 500 particles here. Each particle is independent of each other, so particles do not see other particles that we have simulated here. Nevertheless, our random movement assumes that there are some random hits, other molecules, but it's only a question of modeling. So we do not have real collisions. So, alright, our results. You can now see here's lots of values as tables, but you can always see all these tables also as plots, plot section. And what we see here is the residence time, breakthrough curve, how many particles are active, how many reached their target, so on, travel displacement. Yeah, and finally, we can also use this compute chemical reaction here, and then type reaction rate constant. I will take 50 here, just a guess. Maybe the reaction is faster or slower, I don't know, but yeah, just try it out, hit apply. Then you will see you have another plot here, which says reaction statistics, and which will tell you how much residual species is going out at the end of your channel. You for sure see that here's a mean value of about 20%, and you change your reaction rate, for example, to 100, then so your residual species will go down because your reaction is now faster and can react, all the particles can react a little faster, so nothing, or the material left at the end is going down. Yeah, and it's in principle how you can do it. It's just more complicated if you go to the details, but I hope I could give you some insights of how to simulate molecules and reactions.